Okay, Warriors. Here's the last large group for the semester. So we've been talking about how do we know the exact age of Earth, and we started off with relative dating, and we learned 4 laws for relative dating, which is just older than, younger than, right? So first off was law of superposition that says the layers at the bottom come first and the layers at the top are younger. So you have to lay down layer D, F, B before you can lay down the next ones up. We also learned about lateral continuity. Lateral continuity is how you know that A used to be one piece and G used to be one piece and C used to be one piece because they go sideways in one piece. Original horizontality says that they were laid down in this horizontal direction before something else can happen. So this tilt of these layers comes last after those layers have been laid down. Cross-cutting is what tells us that this valley right here came after layers C, A, and G, and then and so that's how we know this came last, is because of lateral continuity. So cross-cutting always goes with lateral continuity. The other challenge is when you have a layer like E. E then forms this beautiful kind of zigzaggy shape that we can see, or you can look at these little like kind of triangle shapes. And so that tells you that there's some lateral continuity. E is using that valley H as an edge, and so we know E comes after the valley. And we also can tell superposition-wise it's on top of each of these because of that little triangle bit. And so we learned these laws of relative dating. The problem with relative dating is it's not exact. We don't know exactly when something happens. And so then we went to radiometric dating. So radiometric dating is exact age dating. It uses those radioactive isotopes and their decay rates to tell the ages of rock and rock fossils. It works because of the half-life of a substance always follows that same kind of that same graph shape that we saw when we played with Skittles. And so the half-life is the amount of time being the key word, it takes for half of a radioactive isotope to decay. And reminder, decay is when it pushes out those protons and neutrons to become a stable atom. It does have some limitations. You actually have to have radioactive isotopes present. Because those come from the center of the Earth, not everything always has radioactive isotopes, so if it doesn't have it, can't use it. If it's too young or too old, if you think about how we did those problems, we always made this T-chart where we compared the parent to the daughter, and we were looking for the thing that matched. And so you have to have some of those parent and daughter. If you're up here at the 100% and 0 range, you can't tell how old it is. And some of those objects have really long decay rates, like billions of years. So it could be a while before you get any of that daughter isotope. So then you don't know when that rock was made. Same if you have all daughter isotopes. Eventually you get to the part, remember when we had 0 Skittles left in the cup and we had all of them were in the pile that we could eat. If you're at that point, you don't know if it was sitting there for an hour or a billion years. And so if it's too old and it doesn't have any parent left, then we still can't tell how old it is. And then the last limitation to radiometric dating is sedimentary rock. So sedimentary rock is made up of bits and bobs of other rock. So it's got little chunks and pieces. And so are you taking a piece of that it's made up of? Are you taking a piece of the stuff that glues those pieces together? And so you can't really use radiometric dating to tell the age of a sedimentary rock because it's made of bits and bobs of other rocks. And so then we started to look at, well, okay, so we can figure out how old rocks are to some extent, but then how do we know how old Earth is? So we did a quick review of plate tectonics from your 7th, 8th grade year. And quick reminder that convection currents are what drives plate tectonics. So inside our core, it's hotter, and out here on the edge, it's cooler. And so those convection currents really recycle Earth's crust. So that hot stuff rises and the cold stuff sinks. This slab pull is really what drives that engine. And the core is hotter than out here, and so that recycles our solid crust. And so what that means then is all the rocks on Earth are actually younger than Earth itself because they've all been recycled at some point in time. And so our oldest Earth rocks are only 4.16 billion years old. And we looked at a map in lab last week that showed up in northern Canada how the oldest rocks on our continent were up there. And that is really the oldest rocks on our entire planet. But Earth's age, if you look that up, it's usually around that 4.5 billion years old. It's 4.54 billion years old. So how do we know that it's older than our actual rocks? You can kind of think of it like cells in your body, right? Like all the cells in your body are not the same age you are. You've had cell turnover. Some of those cells die and they get replaced. And so the cells in your body have been recycled. It's not that you're not that old. You are as old as you are, but the cells in your body are not as old as your body itself. And so that's kind of like Earth's rock. Those rocks are younger than Earth itself. So how we know how old we are by our birth date, our birth certificate, right? Because someone documented that. Well, the documentation for our solar system lies in meteors and asteroids. So we're going way back to the beginning of the semester to think about this one. So in the beginning of the semester, we talked about nebular theory, right? We were playing with marbles. We had marbles on a hoop. And when one marble started to go, what we realized was mass made gravity, right? And so all objects in our universe form this way. And we saw even those tiny little marbles, they had mass. And if you put enough of them on the sheet, when one marble went, they all kind of came together. So if enough mass in one spot, it'll still have gravity and it will pull in more mass. The thing that pulled in the most mass in our solar system was the sun. It took almost 99.9% of all the matter in the area. So it really took a big chunk. Jupiter was kind of close. It almost became a second sun. But that last 1% was formed into what's called a protoplanetary disk. So here in this one, what we see is you see that center mass that would become your sun. But notice how it's kind of striped, right? All of those dark areas are places where that matter's condensing in and it's getting cleaned up. So the planets start to form and they clear their orbit. So those dark bands are actually where you're going to start to see planets form. So anywhere you see one of those dark stripes, because they clear that orbit as they start to conglomerate that into the planet. And so that's called a protoplanetary disk. And then what ends up happening is you form your actual planet. So we can see where that dusty bit, that lighter, brighter in that image above would have been left over. So these are areas that didn't have enough mass. So the marbles are still kind of hanging out. And then these are the ones where those orbits got cleared. And we can even see even smaller things that got pulled in but didn't go all the way in because we have all these beautiful moons, right? So it's these areas that we're interested in when we start to think about how old all of these planets are. They all formed at the same time from the same planetary disk. And so these objects that we get from these areas of leftover space crumbs, we can use chemistry and radiometric dating to see how old those are. So that was one of the big deals about going to see the asteroid Bennu. So this is linked in your notes doc. It's about a 1-minute video. Shows us landing on Bennu, where they. It always blows my mind that science is so cool. We can take and land a space probe on an asteroid and then bring back a sample. It's so amazing. And so this happened right after COVID. So in that video, you'll see people wearing masks because we were in that time frame. And then this video shows kind of some of that same example. It's not the same rock as Bennu. It's different. But this one is a 6-minute video, and I'll link that as well. The big idea, though, is that all objects in our solar system formed from that same planetary disk. And so they all formed at approximately the same time with the same materials, and they are the same age. So when we start to look at Earth's age, we can tell by radiometric dating, and because we know they all formed at the same time, we can use that information to tell that Earth is 4.5 billion years old. All right, Warriors. Good luck on finals. Have